Hello friends, welcome to Simulator Tools Available for Logic Gates based implementation tutorial. First of all, let me introduction myself. I am Sreka. I am studying computer science and degree program at UALSA University of Sri Lanka. Let's move into our topic. Logic Gate Simulator Tool. First, First, we need what is the Logic Gate Simulator tool. Logic Gate, Logic Gate Simulator is an operation tool for experiment with and learning about logic gates. These are examples for Logic Gate Simulator: Logism, Seeded Logic Simulator, Logic Friday, Deeds. But in this video, I am going to use Logism Simulator. Now we see what is the Logism Simulator and its installation. What is the Logism Simulator tool? Logism is an educational tool for designing and simulating digital logic circuit. This Logism Simulator can runs under Linux, Mac OS and Windows operating system. These are features of Linux. These are features of Logism Simulator tools. Design circuit using an intuitive graphic interface. Watch the graphic be simulate as they are drawn. Build circuits from truth table using conventional analyze module. We can download from SourceForge. You can able to see the web page like this. If you want download it, click on the green color button and we will download Java environment. Now we can go simulator windows. This is our Logism Simulator window. These are menu bar. These are menu bar. These are toolbar. These are explore panel. These are aptitude table. This canvas. We are discuss about combinational circuit. Basically, combinational circuit is a circuit whose output is depend in the present input. Basically, this is a logic circuit. This is having different gates and doesn't have any memory. That means this circuit doesn't have any previous state. It can n number of inputs and m number of outputs. That means you have n number of inputs for the combinational circuit. You may have m number of outputs. This is a block diagram of the combinational circuit. See here, I input n number of inputs and I get m number of outputs. These are best example of combinational circuit: adder, decoder, subtractor. Next, designing step for a combinational circuit. Here, first step is observe the problem carefully. Next, we need consider identify how many inputs and outputs. Then make a truth table and K-map. From K-map, we get problem by related functionality. That means we get a Boolean expression. So finally we can draw a logic diagram from Boolean expression. Here I am using a small example. My question is design a combinational circuit with two inputs which produce output as logic 0 when any one input is 1. This is my truth table. I take two inputs and I get one output. This is my Boolean expression y equal a bar into b bar. Now I am going to implement my logic diagram. This is my logic diagram. Now I am going to check our truth table. First is a equals 0, b equals 0. Now I am going to change a equals 0, b equals 0. Now I am get my output y equal 1. So first row is correct. Second row a equals 0, b equals 1. Now I am going to change a equals 0, b equal 1. Here see my output y is changed. Here my output y equal 0. Here a equals 0, b equal 1. Output is y equal 0. So second row is correct. Third a equal 1, b equal 0. Now I am going to change a equal 1, b equal 0. Here my output is not changed. Y equal 0. A equal 1, b equal 0, y equal 0. So third row is correct. Next y a equal 1, b equal 1. Now I am going to change a equal 1, b equal 1. Here my output y equal 0. This is a simple example for a combinational circuit. Now we are discuss about sequential circuit. Sequential circuit is combinational circuit with memory. That means the output of a sequential circuit is a function of inputs and present state of memory element. That means sequential circuit output is depend upon present input and present state. This is a diagram of the sequential circuit. External input, external output. Here, external input are present inputs. External outputs are next state outputs. Here, internal output. Internal output means the present previous output. Internal input. Internal input means present state. Basically, sequential circuit have two classes. One synchronous, other one is asynchronous. Synchronous most different between two classes clock plus synchronous. Synchronous circuit have clock pulsed. Asynchronous circuit cannot clock pulsed. Clock pulsed. Examples of sequential circuit, flip-flop and latches. Now we are going to see how to design sequential logic circuit by using logism. Here I am taking SR latch using NAND gate. Now I am going to implement my SR latch. This is my SR latch. First I am going to check these conditions. S equals 0, R equal 1. I am going to change S equals 0, R equal 1. Here not change. Earlier in state, here not change. That means Q and Q bar not change for S equals 0 and R equal 0. Second one is S equal 1, R equal 0. Now I am going to change S equal 1, R equal 0. Here see Q equal 1, QY equal 0. This called set statement. Now I am going to change S equal 0, R equal 1. Here Q equals 0, QR equal 1. This called reset statement. Now I am going to change S equals 0 and R equal 0. Here the Q and Q are not change because it's when S equals 0, R equals 0, Q and QR get previous state. That means previous value. Now I am going to change S equal 1, R equal 1. Here Q and QR both are 1. But QR is inversion of the Q. So in this state we called invalid or undefined state. In this chapter we are going to see about the decade counter. Decade counter counts 10 different states. That means decade counter count range from 0 to 9, and when come 10 state, it will be go to the initial state. That means decade counter want to go to the 0 value. This counter can go through any 10 states between 0 to 15 can also made because 0 to 15 we get 4 bit. Now we are seeing how to change 0 value after number 9. See the truth table here. Value 9 after 9 10. Here x1 and x3 both are equal 1, but we won't change 1 to both equal are 0. So here I am using a NAND gate. Here x3 and x1 equal, x1 convert to 0. Example, we get another number. Here I get 6. Here x3 equals 0 and x1 equal 1. Here, so this get 1. This value not change. Reset value. This decade counter use only one state possible for x3 equal 1 and x3 equal 1 and x1 equal 1. Now we are discuss about frequency divider. The frequency divider is a module that lower a signal frequency. The frequency will be thoroughly the clock pulsed will be divided by 2 in outputs, that is why called frequency divider. Here our frequency f dash equal f by 2. Here I divide another 2. My frequency f2 equal f by 4. Here f3 equal f by 8. Here f4 equal f by 16. This is frequency divider. In this chapter, we are going to see about encoder. Encoder is a combinational circuit which convert n to the power n inputs into n output. In the example, we put 4 inputs, get 2 outputs. This is a block diagram of the encoder circuit. Now we are looking about 4 to 2 line encoder. This is truth table for 4 to 2 line encoder. Here I take 4 inputs and I get 2 outputs. This is my boolean expression for this truth table. Now I am going to implement my logic diagram. Here, see my boolean expression, my output is a1 equal y2 plus y3, a not equal y1 plus y3. Here I use 4 inputs, but I only use 3 inputs. So here I take 3 inputs. And a1 equal y2 plus y3. Here I want that y2 plus y3. So I won't use OR gate. And also I add y3 plus y1. So here I use another OR gate. I am going to initialize these inputs. This input y2, this y3, this y1, and here see I got 2 outputs. So I am here, I won't got 2 outputs. So 2 outputs. And I am going to initialize the outputs. This A1, this is A note. This is my logic diagram for this truth table. That means 4 to 2 line encoder truth table. Now I am going to change my inputs variables. Now here first state y equals y3 equals 0, y2 equals 0, y1 equals 0. Here I don't consider about y0. So we are consider those things y3, y2, y1. Here I am first row. Here y3 equals 0, y2 equals 0, y1 equal 0. Here all are equal 0, y1 equals 0, y2 equals 0, y3 equals 0. My output a1 equals 0, a not equal 0. Here truth table. Here see my truth table, a1 equals 0, a not equals 0. Now I am change y1 equal 1. Here I am going to change y1 equal 1. See my output a1 equals 0, a not equal 1. See my truth table. Here I am going to change y1 equal 1. Output is a1 equals 0, a not equal 1. Now I am going to check third row. here y3 equals 0, y2 equal 1, y1 equal 0. Now I am going to change y2 equal 1, y3 equal 0, y1 equal 0. See, my output is a1 equal 1, a0 equal 0. Here see, I am going to change y2 equal 1. My output is a1 equal 0, a1 equal 1, a0 equal 0. Last one, y3 equal 1, y2 equal 0, y1 equal 0. Now I am going to change y3 equal 1, y2 and y1 both are equal 0. See, my output is a1 equal 1, a0 equal 1. See, a1 equal 1, a0 equal, see, this is for two line encoder. Now we are discuss about adder. First we see about calf adder. Before we are going to see what is the adder. Adder is arithmetic combinational circuit. Now we are seeing half adder. Half adder designed to add two single bit number. The half adder designed to single bit number without carry. This contain two inputs and two outputs. This is a diagram of the calf adder. Here I put two input and I get two output. This is a truth table of calf adder. Here first we see a equals 0, b equals 0, a plus b equals 0. Here not carry. Next a equal 0, b equal 1. Some not plus 0 plus 1 equal 1. Not carry. Here a equal 1, b equal 0. 1 plus 0, 1. Not carry. Last one is a equal 1, b equal 1. Here sum a 1 plus 1 equal 1 not. Here sum equal not, carry equal 1. This is a logic diagram of the calf adder. Now we are going to how to round the calf adder. First I want to take two inputs. And I am going to label for these inputs. This is A input, this B input. See my logic diagram. Now I am going to using XOR gate. Here I am going to change number of inputs as 2. And I won't use another AND gate. And I get two outputs. This output is Harry. This is my logic diagram for half adder. Now I am going to check my truth table. First condition is A equals 0, B equals 0. Here A equals 0, B equals 0. This output is S equals 0 and C equals 0. Second condition is A equals 0, B equals 1. Now I am going to change A equals 0, B equals 1. My output, my sum value is 1. Harry is not heaven here. Now I am take third condition, that means A equal 1, B equal 0. Now I am going to change A equal 1, B equal 0. My output is S equal 1. Here I am not having any carry. The last is A equal 1, B equal 1. Now I am going to change A equal 1, B equal 1. See, my output is equal 0, Harry equal 1. Next I am going to see full adder. Full adder designed to add two single bit number with carry. This is contain 3 inputs and 2 outputs. 3 inputs are likewise A, B and C in. This is a diagram of full adder. Now we are seeing truth table of full adder. This is a truth table of full adder. This is logic diagram of the full adder. Now we are going to how to implement full adder logic circuit. I will take 3 inputs and 2 outputs. Now I am going to take 3 inputs. Now I am going to label for these inputs. This is input of A, this is input of B, this is input of C. Now I am going to use XOR it. Now I have changed number of input as 3. Now I am going to add AND gate. Here I want add 3 AND gates. I am going to change of AND gates inputs are in 3. we won't add this 3 and get, so I won't use 1 OR gate. Here I won't get 2 outputs. Now I am going to label this one. This is output S. This is output is Harry. Now I am going to check our truth tables. This is my now we are going to check our truth table. Now I am going to check truth table. Here x equals 0, y equals 0, cin equal 0. Here all are 0. My output is sum equals 0 and Harry equal C equal 0. Next, here I am going to check second condition x equals 0, y equals 0, cin equal 1. Now I am going to change cin equal 1. Here output is equal 1, Harry equal 0. Next I am going to change x equal 0, y equal 1, c equal 0. A equal 0, B equal 1, C equal 0. Here output is equal 1. Here Harry equal 0. Now I am going to check for third condition. X equal 0, Y equal 1. X equal 0, Y equal 1, C equal 1. X equal 0, B. Y equal 1, C equal 1. Here my output is equal 0, Harry equal 1. Now I am going to check in fifth condition, x equal 1, others are 0. Now I am going to check x equal 1, others are 0. My output is equal 1, carry equal 0. Now I am going to check x equal 1, c in equal 1. Now I am going to change x equal 1, c in equal 1. Here my output is equal 0. Here Harry equal 1. Next x equal 1, y equal 1, c in equal 0. X equal 1, y equal 1, c in equal 0. Also here is equal 0, Harry equal 1. Now I am check last condition. X equal 1, y equal 1, c in equal 1. X equal 1, y equal 1, c in equal 1. Also 1. Here my output is c equal 0, c equal 1. Now we are going to see about subtraction. Subtraction is a combinational circuit used to get difference between two numbers. Now, half subtraction. Half subtractor designed to subtract two single bit number. Here single bit means 0 or 1. Here this is a diagram of the half adder. This is a truth table of half subtraction. This is a logic diagram of the half subtractor. Now we are going to how to implement the half subtractor in the logarithm simulator. Here I won't take two inputs. Now I am going to take two inputs. Here I am going to label for these inputs. This is A input. Another one is B input. Now I won't use XOR gate. So I am going to gate option and select XOR gate. After I want one AND gate. Now I am going to select AND gate. Here I get two outputs. One is different, other one is barrow. Now I am going to initialize two outputs. This is different D. This is barrow B. Now I am going to check my truth table. First I am going to check A equals 0, B equals 0. Here A equals 0, B equals 0. My different equals 0 and I haven't any barrow. Next I am going to check A equals 0, B equals 1. Now I am going to change A equals 0, B equals 1. Here my output is D equal, that means different equal 1, B equal 1. Here B equal barrow. Next one, A equal 1, B equal 0. Now I am going to change A equal 1, B equal 0. Here see my output D equal 1, B equal 0. Barrow, I haven't no any barrows. Last one is A equal 1, B equal 1. Now I am going to change A equal 1, B equal 1. My output D equal 0, B equal 0. Now we are going to see about full subtractor. Full subtractor used to perform subtraction among 3 bits. It contains 3 inputs and 2 outputs. This is a truth table of full subtractor. This is a logic diagram of the full subtractor. Now I am going to how to implement the full subtractor in the logarithm simulator. This is a logarithm simulator windows. Now I am going to take 3 inputs. This is the input of A. This is input of B. This is input of B in. Now I won't take one XOR gate. So I won't go to gate option and select XOR gate. And I won't take 3 AND gates. and I won't take 1 OR gate. Here I put 3 inputs and I get 2 outputs. The outputs are different and barrow. Here I won't use 1 NOT gate. And also here I use another NOT gate. Now I am going to put the label for my output. This is output diff and D. This output barrow B. Now I am going to check my truth tables. See my truth table here. First condition is A equals 0, B equals 0, B in equal 0. Now I am going to change A equals 0, B equals 0, B in equals 0. These are already in 0. So here my output D equals 0 and B equal also 0. Now second condition is A equals 0, B equals 0, B in equal 1. Now I am going to change A equals 0, B equals 0, B in equal 1. See my output here. My different is D and here I have a barrow B equal 1. Next I am going to check A equals 0, B equal 1, B in equal 0. Here I am going to change A equals 0, B equal 1, B in equal 0. Here my output is also A equals A. That means different D equal 1, barrow B equal 1. Now I am going to check fourth condition. A equals 0, B equal 1, B in equal 1. Now I am going to change fourth condition. A equals 0, B equal 1, B in equal 1. Here my different D equals 0. Here I have a 1 barrow. Now I am going to check fifth condition. A equals 0, A equal 1, B equals 0, B in equal 0. Now I am going to change A equal 1, B equal 0, B in equal 0. My output is D equal 1, B equal 0. Now I am going to check sixth condition. A equal 1, B equal 0, B in equal 1. Now I am going to change A equal 1, B equal 0, B in equal 1. See, I have no barrow and my difference equal 0. Now I am going to check seventh condition. A equal 1, B equal 1, B in equal 0. Here see, my output D equals 0 and B also 0. Now I am going to say subtractor. This subtractor are 4-bit subtraction. First, we want subtraction. Subtraction is nothing but addition of two complements. If I want A minus B, we can get different A minus B equal A plus 2's complement of B. Here 2 complements of B equal 1's complement of B plus 1. Here 1 complement of B also inverse of B. Next I am going to talk multiplier. Multiplier and operation is evaluate to multiplication on 2 bits. This is a block diagram of multiplier. This is truth table. Here I take 2 inputs and get outputs. This multiplier also equal to an operation. In this chapter, we are going to see multiplexer. Multiplexer is used to 2n inputs line and a single output. This is a 2 into 1 multiplexer. Multiplexer also called MUX. Here I take 2 inputs A0 and A1. Here 2 to the power n, this is a 2 into 1. 2 to the power n equal 1. That means 2 to the power n equal 2. Here we can write also 2 to the power 1 equal 2. Here n equal 1. So here I take selection 1. That means selection input 1 input. Here I take 1 output. This is a truth table of the 2 into 1 multiplexer. This is a Boolean expression. Now I am going to how to implement the multiplexer in the Logicium simulator. Here already defined the multiplexer. So I directly use multiplexer. Now I am going to use directly multiplexer. Here I take 2. That means I select 1 bits. So that means I input 1 select option. Now I am going to select 2 inputs. And also I put 1 selection box. Here I get only one output. Now I am going to put the label of the inputs. This is the input of A0. This is input of A1. This also input S. My output is y. Now we are going to see our truth table. Here our inputs depend on the selection line. We put any value of A0 to A1. We check with S. That means selection line. Now I am going to check selection line. Here selection S equal note. I get output y equal a note. Now I am going to select this. I am going to check this one. S equal note. I get output y equal a note. Here S equal note, a note equal 0. Now I am going to change a note equal as 1. See my output. Here S equal note, output y equal a note. Here I am change a note as 1. This output equal 1. Now I am going to change a note equal 0. Here my output y equal 0. Here the output is depend on the S. Here see my truth table. Here S equals 0, y output is a note. Now I am going to change a equal 1. Now I am going to change S equal 1. Here S equals 1, my output y equal a1. Here S equal 1, my output a1 equals 0. Here y equal 0. Now I am going to change a equal 1. Here my output y equal 1. Now I am going to change a S equal 0. My output also y equal a note. I am going to change S equal 1. My output y equal a 1. Now we are seeing about how to implement 4:1 multiplexer in Logician Simulator. This is diagram of the 4:1 multiplexer. This is a truth table of the 4:1 multiplexer. Now I am going to implement the 4:1 multiplexer. Now I am going to take one multiplexer. Here I am going to change select bit as 2. And I am going to input 3 in. Going to put 4 inputs. And take one input for selection line. Here I won't change data bit as 2 because my selection line 2 inputs, that means S0 and S1, and I get only one output. This is my 4:1 multiplexer. Now I am going to see my truth table. Here my input first condition S equal note, S1 equal Note, here I am going to change S not equal 1, S1 equal. Note that condition my output equal D note. First I am going to initialization here my inputs. This is D note. D1. This is D2. This is D3. Here S1 equals 0, S not equals 0. My output Y equal D naught. That means that here S equals 0, S not equals 0, S1 equals 0. My output Y equal D naught. Here D naught equal 1. I am going to change D naught equal 0. See, my output Y equal also D0. That means D naught. Next condition is S not equal 0, S1 equal 1. Now I am going to change S not equal 0, S1 equal 1. That time my output Y equal D1. Now I am going to change D1 equal 1. See, my output Y equal D1. Now I am going to change D1 equal 0. My output Y equal 0. Now I am going to change D1 equal 1. My output Y equal 1. That means my output Y equal D1. Next condition, S not equal 1, S1 equal 0. S not equal 1, S1 equal 0. That time my output Y equal D2. Here D2 also, D2 equal 0 and my output equal 0. Now I am going to change D2 equal 1. See, my output Y equal 1. That means my output Y equal D2. The last condition is S not equal 1, S1 equal 1. I am going to change S not equal 1, S1 equal 1. This time my output Y equal not. That means my output Y equal D3. Now I am going to change my D3 value as 1. See, my output Y also 1. That means my output Y equal D3. Now I am going to change S1 and S1 and S not also 0. My output is equal 0. That means my output Y equal D naught. Now I am going to change S not equal 0, S1 equal 1. My output is D1 equal 1. That means my output Y equal D1. Now I am going to change S not equal 1, S1 equal 0. My output is Y equal 0. That means my output Y equal D2. Now I am going to change D2 as 1. See, my output Y equal D2. Now I am going to change S1 equal 1, S not equal 1. My output, this time my output is Y equal D3. Here I am going to change D3 equal 1. See my screen, my output is Y equal D3. Now we are going to see applications of multiplexer. These are application communication system, telephone network and computer memory. Next we are seeing demultiplexer. Demultiplexer has only one input and 2 to the power n output. That means here I put one input, I will take two outputs. This is a diagram of the demultiplexer. This is the truth table of the demultiplexer. That means 1 into 2 demultiplexer. This is a Boolean expression. Now, I am going to implement the demultiplexer in the Logicium simulator. Here already in demultiplexer. Now I am using demultiplexer. Here I put only one input and I will get two outputs. And I also put select line input. Here I am putting select line input. This I am going to label this input. This is input of A. This is selection line S. This my output is Y1. This is my output is Y0. Now we are going to check our truth table. Here is equal note, my output Y0 equal note, Y1 equal A. Now I am going to change S equal note. A, here I am change A equal 1. See my output Y1 equal A. Here Y1 equal A 1, that means A. Now I am going to change A equal 0. See my output Y1 equal 0. That means when S equal 0, my output Y1 equal 1 and Y0 equal 0. Now I am going to change A equal 1. See my output Y1 equal 1, Y0 equal 0. So when we are put S equal 0, we get output Y1 equal A, Y0 equal 0. Next condition, S equal 1. Now I am going to change S equal 1. When we are put S equal 1, we get output is Y1 equal A, Y0 equal A, Y1 equal 0. When you apply S equal 1, we get Y0 equal A, Y1 equal 0. Now I am going to change A equal 0. Here my output Y0 equal 0. That means Y0 equal A. Y1 equal 0. Now I am going to change A equal 1. See my screen, Y0 equal 1. That means Y0 equal A, Y1 equal 0. Now we are going to see applications of demultiplexer. These are applications of demultiplexer: communication system, ALU, scenario to parallel. Thank you to all for watching my tutorial video.